Well, I hope you've enjoyed the work in Module 1, where we introduced the idea of a multivariable function. Specifically, we mainly focused on three physical dimensions. That is, there are 0 dimensions, a point. A point really, even though we make it so we can see it, a point really has no dimensions. And then if we move perpendicular, well, if we move left and right away from a point, left or right away from a point, you create a line segment in this case that is one-dimensional. And if you move that line segment up or down, as I draw on this thing, you create 2 dimensions. And if you move that 2 dimensions kind of front and back, you create 3 dimensions. And so that's what we've been focusing on here, is trying to represent three-dimensional things or multivariable functions in multiple ways. And I'm talking about dimensions as I draw this picture from 0 to 3 dimensions, but I want you to imagine that it doesn't have to be physical dimensions. It could just be multivariable quantities. That is, 2 input quantities produce a third output quantity. How could we represent that? Well, you've seen, I'm sure, a map like this before, where you might imagine a location, an input, like say a latitude and longitude, gives you a location on the map, and then the output, the third dimension, produces the temperature at that location. So input a location, latitude, longitude, output a temperature at that location. So 3 dimensions, we just show it in a 2-dimensional drawing using this color coding idea. And they do that with the numbers and color coding as well here. And you can see like everywhere in this pink band up here, it's around 15 degrees. Everywhere in this orange band down here, it's 75 degrees. Here's just a few more. We see these things. If you just Googled, these are called contour plots. It's a 2-dimensional representation of a 3-dimensional situation. The 3 dimensions in this case, let's see, west longitude, north latitude, and then each of these contours, or we call them level curves. Level curves because everywhere on this level, the output is 6% Hispanic in McHenry County, Illinois. Or, let's see, this is Hudson County region. This is a topographical map. I'm going to get to another one later. Baroclinic gravity wave phase speed. I don't even know what that means. There's 5 words there that I've seen before, but putting them together, I don't know what that means. And so I just wanted you to see, you Google, there's all kinds of imagery about this idea of multivariable functions. Imagine this. Here's the Half Dome in Yosemite National Park. And if you were to think about a topographical map at the Half Dome, you can see some things. So the way we did this one was we put an origin at Mirror Lake. So you could travel in the traditional coordinate system in the X direction, the Y direction, but then at any location in this map, we get a Z, which is an elevation. And notice we've scaled it by 500s, which is a common thing. Pick a scale. So we scale by 500s. And there's features about this 3-dimensional situation. Remember, it's representing this area, this region, and we represent that 3-dimensional geography using a 2-dimensional topographical map, a contour plot. We see like here, there's that sheer face of the Half Dome. You see that, remember, scaling by 500s in terms of elevation, very small changes in X and or Y produce 500 feet change in elevation. So very, very steep. When you see these level curves very tightly packed, we know that there's a very steep topography in that area. Or if you see like a loop here, 8,500, so you're at the top of a mountain. At the top of a mountain, we don't see dramatic elevation change, at least not enough to produce another 500 feet and warrant another level curve. So things are a little more flat in here, not much change compared to in here. So that's what you've been studying for a while, and now we're going to move this unit to several mathematical things, but for this opener, I want to focus on what might be the most challenging of them all, and that is the idea of limits and continuity. And I want to just remind you of how it worked in Calc 1 a little bit and then extend it to Calc 3. So in Calc 1, you may have had a situation like this, a two-dimensional single variable function, y is a function of x. And you had a situation maybe like this, and then an open circle, and maybe like that, something like this. And at this value of x, we'll call it a, we would say things like this. The limit as x approaches a. Now, because we're just moving in this one-dimensional direction along the x-axis, you can approach a, or the value of x can approach a from the right or from the left. And then we would say, what does the function do as x approaches a from the right or the left? Well, as x approaches a from the right, let's say this was at 1, and we'll put this one at 2, just for something to talk about. So we would say as x approaches a from the right side of a, this function wiggles its way towards a function output of 1. But as x approaches a from the left side of a, the negative side of a, this function winds its way towards 2. Now, because the limit from the right and the limit from the left don't have the same value, what we would say is the overall, the two-sided limit as x approaches a of f of x, we would say that that limit does not exist. And because of that, because the limit does not exist, we also can claim that there's a discontinuity at x equals a. Now, I hope all of that, there's some just-in-time videos in the modules about limits in Calc 1, but I just wanted to give that quick overview. I hope as you're hearing this, your head is nodding like, oh yes, I remember about that. How does all of this look, sound, and feel in a two-variable, three-dimensional situation? So now you'll notice here we've got a function of two variables, x and y, producing a third dimension, an output value of z, or f of x, y. And so we have to imagine not just x approaching something, but notice it's a function of x and y. And notice this function is defined such that when x and y are not 0, we can use this function over here. But when x and y are 0, 0, then the function outputs a 0. But now here's the deal. How do we represent limits in this case? It's not just x approaching 0 from the right or from the left. Also, y could approach 0 from above or below. But not only that, but x and y could approach 0, 0 from all kinds of directions. This is the interesting dilemma as we just expand one more dimension to a three-dimensional world, two-variable input. We have this issue with limits that it's not just one variable moving along a one-dimensional number line. We now have two variables moving in a two-dimensional plane. So here's how we represent this. We now have to say the limit as not just x approaches, but as the ordered pair xy approaches, and in this case 0, 0, and not just f of x, but f of xy. And again, what we're looking for is, does this, as we imagine the ordered pair xy getting closer and closer and closer and closer to the origin, does the z value have a limit? Like, does it all blend into one place, or is, depending on how you approach, does the z value hit something up here, hit something down here? Well, let me just show you what this would look like. In the case of f of xy, oops, wrong way. In the case of f of xy, here it is. As x approaches 0 from any which way, and as y approaches 0, and as xy together approach 0, 0, to be right about in, 0, 0, 0, yeah. So xy 0, 0, 0, it's hard to represent this. There's 0, 0, 0. So no matter how xy approaches 0, 0, it appears as though the function is defined, or the function is outputting values closer and closer and closer and closer to 0, 0. And at 0, 0, the function is defined to be 0. So we can see this now that it appears that we have a nice continuous flow here in this case. Now, what about this one? Notice in this case, we made a small change to the numerator. X squared times y, just x squared. Similarly, though, what we're thinking about is as the ordered pair xy approaches 0, 0, from any which direction, infinitely many directions, how does the function g of xy behave? Does it all blend in towards 0? I'm going to fill that in. This one, it seems from our graph that the limit would be 0, and f of xy is defined to be 0 at xy equals 0, 0. And so we have this nice continuous flow in this surface at 0, 0. But what about g of xy? Do we have a similar feel or not? Are you ready? Here it is. So as x approaches 0 from any which way, as y approaches 0 from any which way, as they both approach 0 from any which way, notice what's happening here. Instead of a break or a hole in the graph or an asymptote like you would have seen before, this particular graph, we get a tear in the graph. I mean, I don't mean a physical tear, but that's what we call it. It looks kind of like the graph got torn there. And depending on how x and y approach 0, 0, we could output values up here closer to 1, or we could output values down here closer to 0, or somewhere in between. And so the limit doesn't even exist, because depending on how xy approaches 0, 0, z could be closer to 1 or z could be closer to 0. You've got this disconnect, this discontinuity at 0, 0. And so back to this, we say this limit does not exist, and we see a discontinuity at 0, 0. Now, if this whole limit conversation is like, you might just go back and take a little time, just-in-time videos in this module related to single variable, just x approaching a value from the left and the right, and then jump into the module and see how does this limit thing work in a multivariable world. I wanted to use this video just to visualize things and connect it back to Calc 1. Hope that helped. But continue studying and thinking about this in this module. Have fun.